Good morning. This is the last session of our module 3, experimental methods and error analysis. Okay, with this section we will complete our module 3. So today we are going to learn about standard deviation, which is an important session. So usually all measurements that we make with instruments, there will be some error, but it is not possible for us to determine the error accurately, and that error involved in the measurement will be reflected in our results. So for example, if you are measuring the time intervals using stopwatch, definitely there will be a reading error. Okay, but however that error is negligible, that is you can ignore it when compared with the other errors that is possible in the measurement. So in order to estimate the errors, what we do is we repeat the same experiment a number of times, and then we take the average or the mean value of the readings that we have taken. Okay, so let xi be the value obtained in a single measurement, and let x bar be the average of the different measured values. Then let n be the total number of measurements made. Then the average of the n measured values will be, that is you quite know well, that is x bar is equal to 1 by n sigma of xi. Now xi minus x bar, that is the measured value minus the average value of all measurements, is called di, that is deviation. The standard deviation is represented by the letter sigma. It is given by square root of 1 by n minus 1 sigma di square, or root of 1 by n minus 1 sigma of xi minus x bar the whole square, because di is actually xi minus x bar. Now the standard deviation thus gives us an idea about the average spread of experimental results about the true value or about the mean value. Now they have given one more example. They have measured the time period of a simple pendulum, just like that you have measured in your lab: 2.9, 2.5, 2.7, 2.4 and 2.5 seconds. Now they have taken the average period or average value x bar, that is they are just adding the numbers obtained divided by total number of measurements, that is 5. So they got it as 2.6 seconds. Now their next aim is to find the average deviation, that is you got the value, the x bar value is 2.6. Now we have to, in order to calculate the deviation, what was the formula? You have to subtract this average value from each of these measurements, that is 2.6 minus 2.9, that will be minus 0.3. And this, okay, that is, in order to find the deviation you have to subtract the measured value from the average value. Okay, so here the measured value is 2.9, first value, average value 2.6. So 2.9 minus 2.6 is minus 0.3. Then 2.5 minus 2.6, that is minus 0.1. Like that you have to subtract each of these measured value from the average value, so you get the deviation values as these. Now the average deviation you have to add all this. On adding, you are getting the average deviation as 0. However, some why? Because that you have obtained some positive values and some negative values, so they will get cancelled each other, and that's why you're getting the average value as 0. So in such cases you will not be able to estimate the error. So in order to overcome that value, what you do is you just take the square, so the negative values will become positive. So we use, instead of finding deviation, we use standard deviation, which is nothing but the square of deviations are taken and the square root is found. So how will the standard deviation look like? As per the formula discussed earlier, it is sigma equal to root of 1 by n minus 1 sigma di square. So here 0.3, the square 0.09, negative 0.1, on squaring it will become positive value 0.01. Like that you have to square each of these values, and then finally taking the square root as per the formula, you got the value of standard deviation as 0.2. Then you write the final result, that is the period of simple pendulum, that is the average value that you got already 2.6. It can be plus or minus the standard deviation 0.2. So this is the result, that is 2.6 plus or minus 0.2 seconds. That is just an example. So now what is the significance of standard deviation? That is If we know one more measurement using the same apparatus, that is what it is said in this paragraph is that as long as you repeat the experiment so many times, the possibility of reducing the error involved will be high. So here they have given with the help of a histogram, that is 200 measurements of a quantity is made, then the mean value was found to be 10.5 and standard deviation was 1.83. So here they have shown a histogram of 200 measurements, that is in 25 of the measurements the value was in the range 9.5 to 10.5 and most of the readings are close to the mean value 10.5. C. Here for large enough sample, about 68% of the readings is well within that limit. Okay, so the smooth, here you can see everything is coming under that loop. So about the 95% of the readings will be in the mean interval that is already calculated. So this curve, actually the histogram is actually a smooth curve superimposed, and it has got a distribution named as Gaussian or normal, and as more and more measurements are made, the histogram will have the shape of a Gaussian curve which is bell shaped. However, standard deviation of distribution will remain the same. So this is how, here you can expect a question, what is meant by a histogram. Next is the calibration of instruments. Calibration is nothing but a process of establishing a relation between a measuring device and the unit used to make the measurement. Now, how this is done is that we need the device that we have in hand is compared with the standard one which have non-measurement. So calibration is done by comparing the device with a standard having non-measurement characteristics. For example, a rod is calibrated to measure length by comparing it with a standard which has a non-length. The device with a known correctness is called a standard. Once a relationship is established, then the rod that we have can be used to measure unknown lengths. So for the purpose of calibration, the main aim of calibration is used to maintain the quality of measurement as well as to measure the proper working of particular instrument. Now the outcomes are given here. No significant error being noted on the device under test. Sometimes a significant error will be noted, however you are not making any adjustment. Sometimes an adjustment will be made to correct the error to get a desired result. So calibration, in other words, we can say it is an act of comparison and does not include any subsequent adjustment. So it is not adjustment. Okay, so it is just in simple words we call calibration as adjustment or trimming, but actually it is not adjustment. We are just comparing the device that we have with a standard one whose measurements are known. Okay, some calibration is required under which all situations, that is when you are using a new instrument it has to be calibrated, then after an instrument has been repaired or modified it has to be calibrated or corrected, then when specific time period has elapsed then you need calibration, when a specified usage or operating hours has elapsed you need calibration, then before and after a critical measurement you need to calibrate the device. Then after an event, for example after an instrument has been exposed to shock or vibration or any other damage, it has to be calculated for its better performance. Then in case of sudden changes in temperature, when an instrument indications does not match the output of similar instruments, then as per customer specifications or instrument manufacturer recommendations we need to calibrate. Okay, now various types of calibrations are there. Calibration is done at different points of measurement, okay, instead of calibrating at each points. So a particular points are selected and those points are calibrated with an expectation of error. Okay, now these type of calibrations are single point calibration done over a single time. Then there are 2-point, 3-point calibrations based on the number of points at which calibration is performed. So if you are performing the calibrations only at one point, it is single point, otherwise it is 2, like that. Now let us discuss about a few calibration errors. Some of them are zero shift calibration error, span shift calibration error, linearity calibration error and hysteresis calibration error. So here The slope intercept form of a linear equation that describes the response of a linear instrument is given by y is equal to mx plus c. This equation. Here y is the output, x is the input. C is zero adjustment and m is span adjustment. Okay. Now zero shift calibration error. Its definition. A zero shift calibration error shift the function vertically on the graph as you can see here, and it is equivalent to changing the value of c in the slope intercept equation. This error affects all calibration points equally, creating same percentage of error across the entire range. So here you need to study only the definition for zero shift calibration error with this diagram. Next is span shift calibration error. It actually shifts the slope of the function, which is equivalent to altering the value of m, because m actually stands for span adjustment. Okay, in the slope intercept equation, this error effect is unequal at different points throughout the range. Okay, then you can write that paragraph and draw this figure. Next is linearity calibration error. It causes the instrument's response function will be no longer a straight line. It does not directly relate to a shift in either zero span, but because slope intercept equation only describes straight lines. Now this behavior of linearity adjustment is unique to each instrument, and if you want to make it more accurately calibrated, you have to consult the manufacturer along with its documentation. And then however, this linearity calibration error can be eliminated only in this way. So just describe the first paragraph, then I think you can write these two paragraphs and the diagram. Next is last one, hysteresis calibration error. It occurs when the instrument responds differently to an increasing input compared to a decreasing input. Now the only way to find out this error is to do an up-down calibration test, that is checking for instrument's response at same calibration points. Now hysteresis errors, they are always caused by mechanical friction on moving elements or loose coupling between mechanical elements. So they cannot be rectified by simply making calibration. However, one can replace those components with a good one or correct it according to the needs. So most of the calibration errors will be a combination of either zero, span, linearity and hysteresis problems. Zero errors always accompany other type of errors. So technicians often perform single point calibration in order to check the calibration health of the instrument. If the instrument performs within specification at that one point, then its calibration over the entire range is probably good. Okay, if it does not meet the specification at that point, then it needs to be recalibrated. So with this video I will upload a few problems from this error analysis part and also some questions also for your reference. Okay, thank you.